over here in KL, it's quite a nice morning. We have a lot of sunshine. So let's get started with let's continue with this lecture on fuzzy expert systems. Any questions from the previous part? Can I also check with some of you to maybe just say something so that I know, at least I know my headphones are working. I think you can hear me. I think I can see the microphone is working, but the only thing I'm not sure is whether my
yes, sir, can hear.
Thank you. Okay, I think we're all set to go. So let's continue. So now we are trying to look at a case study whereby we want to build a fuzzy expert systems, or in other words, a fuzzy inference system, or FIS. So in this case study, what are we looking for? What are we trying to do here? So this is supposedly quite a large or maybe medium-sized service center. So the service center will keep spare parts. Now, then the parts which are broken will be repaired, or the failed ones will be repaired. So there are two things here. So you keep a stock of all the good spare parts. And then those parts which are not working, you try to repair them. So the process itself. Now let's look at the process. The customer brings in a failed item. So in exchange, he or she will receive a spare part of the same type. Furthermore, the failed parts as a result will then be repaired, because you want to ensure you have enough good parts to give to the customer. So then once the failed parts have been successfully repaired, they will be placed on the shelf, and then thus therefore will become the spares, the new ones, for the others to take away. So the objective of this system, what is the objective of you trying to build this system? The objective here is to advise a manager of this service center on certain decision policies to keep the customers satisfied. So if you look at it, it's a very simple objective. You want to keep your customers happy, right? So what should the manager do to ensure that? So the manager ensures that all his or her customers are always happy, right? Because if the customer receives complaints, right, so it's an indication of the quality of your service center. So the manager is given a very simple task. What should I do? What is my strategy to actually ensure that my customers are satisfied? And also as a result, once they're satisfied, you should be happy. So with that, 4 key points for the system you'll be building. So now we come to the next stage. What is the process of developing a fuzzy expert system? As you can see here, there are 5 steps. The first step is you specify the problem, and then you define your linguistic variables, right? So you can still remember, we're looking at the customer satisfaction, we're looking at the spare parts, the number of spare parts to keep, and then maybe the repair of your failed spare parts. Then once you're able to specify the problem and define your linguistic variables, you then define your fuzzy sets. Step 3, you elicit and construct your fuzzy rules. So this is the part you have to figure out, how should I construct the appropriate fuzzy rules. Encode the fuzzy sets. So in your system so far, after 3 steps, you should have the fuzzy sets. You should have your fuzzy rules and the procedures. So you can now encode them to perform your fuzzy inference through the expert system. Therefore, you have your fuzzy expert system. Now, after these 4 steps, normally it should be finished, complete, go home, back up, right? No. In the first run, The first time you're doing it, the first pass, the system performance may not be that good, right? Of course, you can be very lucky, and the first time you get something close to what you want. But as I said, normally from experience, you won't get. You can still improve it, even though you get close to what you want. You may want to try, push it further to get better results. So that's why you have step number 5, whereby you then test your system, measure the performance of the system. Based on this set of data, you test your system, would the customer be happy? So system will tell you what you should do, and then the customer should be happy at this level. Very happy, not so happy, or unhappy. Then you try to measure that, compare that against the actual, maybe the actual customer satisfaction. Depending on the gap, you will have to fine-tune your system, improve the system further. Right? If it's not so good, you of course make sure it's good. Right? So depending, then you play with all the other parameters that you have in terms of the membership, in terms of the sets. So let's look at the first step. You specify the problem and define your logistic variables. So from this problem that we have the number of good spare parts that you keep. Then you have your failed parts that the customer brings in for you to repair, and then turn around to become good parts for you to give to the next customer coming in. So based on that problem, right, you have your, it is suggested you have 4 linguistic variables, right? What are they? The average waiting time, called mean delay of M, right? It means that how long you have to wait, right? The customer have to wait. Repair utilization factor of the service center P. So basically about how well you repair the parts. Number of servers, right? As a repair center, as a repair center, you will be servicing your customers. So you need to have sufficient number of servers. That will also affect your waiting time. Right? You can see here now it's a balance now. If you have more servers, waiting time maybe less compared to insufficient servers. Of course, they're also dependent. The waiting time is also dependent on your number of spare parts that you have. Of course, in this system, you need to start with something first, which is your initial number of spare parts. Right? If you have a sufficient number, then the repaired one will keep coming in, right, to exchange. So it should not run out. So there are 4 things here. 4 linguistic variables: the mean delay, the repair utilization factor of your service center, number of servers S, and also the number of spare parts N. So now based on these 4 variables, so now let's look at the first one here. So the call it a $1 million question would be, how many linguistic variables you want to have to represent, right? Your, for example, mean delay. Maybe for the first run, you try just 3 first. Of course, you can't get anything smaller than 3. 1 is out of question, right? So it doesn't make sense. So of course, the more the better. But of course, is it necessary to have many? If you have many, what's the downside? Downside is you have to do more calculations, which will slow down the system. So in this case, we have try with 3. So mean delay. So logically, we will have a very short delay, and medium delay. Medium, short, very short. Now, some of you may not realize this. Again, this is actually testing. I also see that in some of your work that some of you may not understand what you're trying to do here. So in this case, if you're looking at the mean delay, my question is, why isn't there anything for average, long, and very long, or extremely long delay? Right. So logically, you know that yes, you should to be complete, way to complete, you should have the other types of linguistic variables with hedges, vary and whatever. So you can have also long, you can also very long, right? Or even extremely long, right? But does it make sense? imagine, I think you all know that if the delay time is very long, definitely your customer will not happy. So don't even need to consider that. So that is your strategy. Do not even need to consider that, right? Long, very long, and things like that, not large or very large, right? Because you know that it will not work, right? It's in a way, what is this? Is this again common sense way, right? So we have, so we have only these three. Of course, you also want to have a very, very short, right? So very, very short, yes, it's also good because it makes sense to have very, very short delay time, but is that possible? Right? So we'll come back to your what I call your how well do you think your system or your service center can have can actually bring the delay time to very, very short, right? To bring that to very, very short, yes, it's good, but then what is the capability of the service center in terms of the resources that you have? Do you have enough resources to actually look at very, very short delay time? So again, that's why for the start, don't put it there first. Or even later on, again, you can see here, even later on, you may not want to consider that because you have to also, as a system developer, you also need to know, again, it depends on your range, on the range itself. Of course, you can see 0, actually the range is actually, you can see 0 to 0.7, right? So I believe that in this example, in this case study, all the values here have been normalized to 1, between 0 and 1. So if you want to have very, very short, you still can, but then you just break it down. Very, very short is defined as 0 to maybe 0.15 as an example, right? You break it down, so it's still all right. So moving along, we have a number of servers. So number of servers, you have a large team, a medium team, and a large team. So you can see here, we don't have a small or very small, it doesn't make sense again. So again, when you design your system, you have to also make use of your own intuition, what you think the system should have, right? So as I said just now, it doesn't make sense to have large waiting time and very, very large delay for your system. So those things you want to consider, right, for that. So in the number of servers, you have a small, medium, and large. So again, it's broken up into 0.35. Then here you can see the bit of overlap, 0.35 and 0.3, so overlap between small and medium. In this case, the large overlap also, you can see. Very short is goes from 0 to 0.3, very short is goes from 0.1 to 0.5. You can see there's an overlap here. The next one, utilization factor. Repair utilization factor, I suppose it's about how frequently, how well does your customers uses the turnaround, uses the repair items. So in this case, the linguistic variables value to range from low, medium to high. The utilization factor is high. The utilization factor is low. Utilization factor is medium. So again, you can break it into 0 to 0.6. Again, overlap. See here, this is also the trick here for you to actually, there's no hard and fast rules for you to say, this one can see all of these three here have three linguistic values in a way. You can see they are actually different, right? Different ranges of values. These are actually overlap a lot. 0 to 0.6 and then 0.4 to, and then from 0 to 0.6, 0.4 to 0.8, 0.6 to 1.0. Whereas here is a bit different. This one is a bit conservative, only 0 to 0.3. And this is even more conservative, 0 to 0.3. And finally, the number of spares. How many spares do you want to keep? Again, reflect back using your, as a designer, as a developer, use your experience, use your intelligence to look at it. Because if you have a high number of spares, you need to at least initially start. You need to invest in a lot to keep those spares. But if your car, if your system equipment actually is a high quality, it doesn't break down. So the number of customers coming in to exchange their broken parts are not high. Right? So you have to look at those things. Is it high or low? So number of spares. So we look at a very small number of spares, keep just enough to turn around. So all the time, maybe your warehouse is zero, don't have any, one or two only, doesn't have a lot of spare parts, but it's just ngam ngam like they say that, so it's okay. Then you have things like small, rather small, medium, going to rather large, large and very large. So this one can see have a higher resolution, right? As compared to the earlier ones, only 3. This one is actually now it's 7, so it gives you a better resolution. There must be a reason why to do that. Of course, this is actually either you think of it yourself, or you can talk to the expert and say, this one you should have a higher number of linguistic values, so that can give you a better control of your system itself. So with that, now we move to the next step. The next step is to determine your fuzzy sets. So as I think this one we're actually talking about, as you know, well, I think all of you will have, except one group, will have finished your lab number 3, module number 3, which is actually to explore the fuzzy toolkit. So you know that the fuzzy sets can have many variety of shapes, ranging from your trapezoid, triangle, right? So the triangle or trapezoid can often provide an adequate representation of the expert knowledge. So using the triangle, trapezoid, or even the Gaussian, right, is sufficient to represent the expert knowledge. At the same time, these fuzzy sets can also significantly simplify the process of computation. Notice that when you use triangle, trapezoid, these are the mathematical simplification of the actual, for example, or Gaussian, or something much more complicated. So this one is simplified. So when it's simplified, the computation is faster, so the system will react faster. And most studies have shown that your mathematical simplification is sufficient for you to model the actual representation. Instead of using those complicated shapes, this will be a simpler and sufficient representation of the actual knowledge. So if once you've done that, right, based on those earlier values, over here, now we can actually draw out, show it, visualize it, what they are. So with that, you can actually maybe fine tune it and see whether you can see here, for some reason, the expert, the system developer, feels that you shouldn't have equal amount of overlap on the left and the right. Notice here, the overlap on the right hand side actually is smaller compared to the larger one. On the left hand side, sorry, it's larger on the left hand side. Why? So it's up to the designer. There's no reason why, except that maybe for some reason the system developer feels that this one works better. So this one is up to us to play with it. It's a bit of a variation you can have in developing the system. Number of servers, instead of the left hand side larger than the right hand side overlap, now it's reverse. The right hand side overlap is higher than the left hand side overlap. Yeah, this one is actually sitting right at the center, number of servers. Right? Have a small number of servers, a medium and a large team. This is all normalized, the same 0 to 1. So again, this is quite flexible in the sense that you can actually do it for quite a large number of different systems, because if we say my value of 1 actually represents 100, and you can play with that. Repair utilization factor. Now notice that the left hand side is actually larger now, right? The fuzzy set of the low utilization is larger compared to medium and high utilization. Again, there's no scientific rule to say that it must be larger here or can be larger. So you have to play with that to actually move it around to actually improve the accuracy of the system. Finally, you have your number of steps. Again, I think in your assignment, I also showed you a paper done on the iris flower. The paper was actually, the work was done by a researcher from Iraq. I can see that she actually gives a quite okay, unconventional and not standardized range of values. See here, they're all different. They're all the same shape, which is actually a triangular at the soil, but you can see the width of the amount of overlap between each of these actually as what do you call it? So it's rather than saying that left hand side and right hand side are the same, I can see it's a mirror image of the other side. The amount of overlaps actually and the size of your linguistic variable value is actually not standardized. I can see a bit of overlap. More. This is very large base, and this triangle is also very large base and so smaller base and so on. You can see. So now, once you've done the membership sets values, now construct rules. So to accomplish this task, you might ask the expert again to describe how the problem can be solved using the fuzzy linguistic variables that we have defined previously here, right? So it's like based on these values here, what should I do? What's the rule? So the required knowledge can also be collected. So other than talking to the experts, right, you can also get information from other sources, such as books, computer databases, flow diagrams, and observe human behavior. And of course, the experience of the developer, the system developer, to actually look at the system here. That's why in your FYP, you can also talk to the human expert. You can, but not. We encourage you to look at the prior work, literature review, what people have done before, and then from the published report on their work, maybe you can find some new information for you to better design the system. So now we have that. We now want to represent each of these linguistic variables with symbols, right? Very short represent VS, short is S, and medium is N, and so on and so forth. This is the representation of the linguistic values in the notation form, rather than this very long sentences, long words. So now this is your fuzzy associative memory of fact. Not the Football Association of Malaysia, but fuzzy associative memory. So in this case, any questions? I thought there's something wrong. So the so we want to map, for example, the number of servers and the mean delay. And then if in this case, if the mean delay is medium and the number of servers is small, then it is medium. Let's look at it now. So these are the rules now. So these are the rules that we actually created from that early on set of values and your and the input values, input variables. So here you can see. So this is basically by default. By default, actually, it is a n function. So this detailed analysis, which is derived of the service center operation, was designed and developed with the in consultation with expert, right? And then as a result, it resulted in 27 different rules, right? So you can see here, you can see rule number 1 is the so I think the output is your number of spares you should keep. So this one actually the system. What's the output of the system? I think we've not discussed that. The output of the system is actually how many spares should I keep, right? Based on how fast do my service team, my technical people repair the broken parts, right? And how many servers do I have? How many people there are? Maybe servers I can also talk in terms of the people repairing the broken parts. So, and then also what is P again? What is P? P is your utilization factor. How frequently are the parts being used or returned back to the customer? So this will then tell you how many parts you should keep in your storeroom. So for example, number 1, if the mean delay time is very small and the number of servers is small, and your your repair utilization factor is large, then you should have a very small number of spares. Right, so it's always I think the assumption is actually in this case it's always n function. So you can see for such even a I would say just a simple problem. You can see that we have 27 rules, right? So this is your rule base number 1, looking at 1 to 12, right? Now, why 1 to 12? 1 to 12 can see here, actually it's here, right? So you can see it's only looking at the small and very small. Right? So if the rule number 1, if the utilization factor is large, then your number of spares is small. If the utilization factor is medium, then the number of spares is medium, and it goes on. And you look at the then your two inputs, which is a mean delay combined with number of servers, then again recommend to you how many spares you should keep. Then you have number of mean delay is okay. This is number of servers is small. You can see blocks of 3. This 3 will be number of servers is small, number of servers is medium, and the mean delay ranges from very small to medium. The last one here actually is a number of servers is large. Right. So that. So with that, you can also visualize it. That is nothing more than just visualizing for you to visualize how you build the system. Now let's look at the one of these blocks. So you can see the output will be your number of servers. This is so this is actually will be in this form, right? You have blocks of 3 ranging from this is your repair utilization factor P, ranging from low, medium to high. So this is a 3 dimension based on those 3. Of course, if you have more than 3 inputs, of course then you will be much more tricky to actually represent the 4 dimensions for the inputs. So in this case, just for this case study, you can see that I can represent it this way for me to see, right? Where my rules are and how my rules are formed. So how do you read the rules? Example. So if you look at rule number 7 over here, so you can see rule number 1, 2, 3. Rule number 7, let's go back here and look at this is your, and the dimension here will be your repair utilization factor. Here, rule number 7. Oh, no, I don't have it. Rule number 7 is over here. Right, so you can see, go back, rule number 7 is over here. Mean delay is very small, number of servers is medium, then the spares is number of spares is rather large. Right, so here, this is your representation of the rule base of the rules. Then in this case, see that's small. So basically, in this case will be if the mean delay is very small and your service is large and your utilization is large, then your number of spares is small over here, and it goes on. So you can see it goes on. This is how you interpret and read the rules as you form them, as you develop them. So now moving on to step number 4, you're now ready. Once you have the rules, now you're ready to actually form your system, build the system, implement your system. So you encode your fuzzy sets, the fuzzy rules and procedures to then perform your fuzzy inference into the Excel system. So to accomplish this task, you can choose several options. You can build a system using programming languages such as C, C++, or Pascal, or you can also leverage upon the MATLAB fuzzy logic toolbox or your fuzzy knowledge builder. Now, this is only 2 of them, right? Of course, there may be other systems that you may be familiar, right? But nowadays, there are so many systems out there you can actually build. Of course, the fuzzy MATLAB is actually quite powerful, common, popular, and so is your C++. But C++ may be a bit tricky because you have to do everything from scratch, unless you have your libraries, appropriate libraries for you to help you to develop the system faster. So once you have got the system developed, now the time is now for you to evaluate the performance and then fine-tune the system if appropriate. So the question here from Yao Xing is here. His question is all the input evaluate with a but all input evaluate with S, but is it required to replace other than? Okay, right. So I think basically his question is go back to this cube, right? So basically this is a visualization. What it means is that once you form the rules, I want to see and are there any parts which are missed out. So basically he's looking at the y-axis. Y-axis is here. So y-axis is actually your number of servers. Now number of servers, as you know, we have only 3. I think all of them 3. Number of servers is small, medium, large. So all this is except for your number of steps, which is the output, right? So the inputs will be mean delay M, S is your y-axis, and then P is your z-axis, and your x-axis is your M. So in this case, basically you're forming the rules, and once you form the rules, I want to see what's my mapping, right? Because the rules actually can be quite difficult to actually analyze. So to help you analyze, I want to use this to visualize it. That's all. It serves that only that function. It will not give you a better system, but it helps you to develop a better system because you can see what's my mapping. Maybe sometimes you can see that they actually developed the system wrongly. For example, why they put a VS here, right? Things like that. So again, this is meant much more for visualization, right? To see have you completely mapped the whole problem space, right? That you have for the 3 inputs. So for the cube here, you can see the M is well, X is your mean delay, Y is your number of servers, and your Z is your repair utilization time, right? And give you of course output. Okay, so let's go on. Once you've done that, so now, as I think from the day one, I've been telling you that in building a system, you must always be able to measure its performance, and you must always also measure its performance. Otherwise, you won't know how good is the system. Because the system is no good, then you will not be able to get your users to use it. So the last and perhaps the most laborious, right, painful, a lot of work done, is to evaluate and tune your system, right? We want to see whether our fuzzy system meets the requirements specified at the beginning. Keep your customer satisfied. So you have several test situations. Depend on the looking at this. So you test your system now. So this is so far we're talking about the training, right? Based on this based on a certain set of inputs, after talking to the expert and also looking at the literature, papers and books, you find that this is the best system. But now you want to test it out on the actual values that you have, right? So you want to test it on the base it on to play with different values on mean delay, number of servers, and your repair utilization factor. Again, for those of you who actually have gone through your lab number 3, we have the same thing, right? We ask you to develop a model student system to identify the best student for the year. So once you've done that, you need to test it. So you have to play with few values for inputs. So in this case, you put in some value for mean delay, number of servers, and repair utilization factor, right? So then once you've done that, you can also with fuzzy toolbox, logic toolbox, can also generate a surface to help you to analyze the system performance, right? So it is not necessary, but it is good for you to analyze the system performance by visualizing it using this 3D surface mapping to actually generate what does the surface look like. This is what we have. So we have a number of servers based on this, and then based on these values of number of servers, what will be the output? So this is the surface of your output. We call it performance, if you like, not performance. It's more like how does the system react? What does the system tell you based on a value of 0.4 number of servers, 0.3 or 1.3 number of mean delay, and maybe 0.6 or 0.6 number of spares. Number of spares, is it? Number of spares, number of spares. So this will give you the number of spares you should keep. So based on these two, what is the output? What does the output looks like? The system output looks like. You can also do it for the rule-based number 2, and now you actually base it on this is the actual output. So if you have a 0.4 to read this, if you have a 0.4 mean delay and a 0.2 number of servers, what does the system, how does the system perform? What's the output of the system in terms of number of spares? So this one actually you can actually plot. The system will, if you run up this 3D plot, it will tell you what is the recommended value that the system will give you based on say 0.4 and 0.2. So give you something over here, right? So give you some values over here. So you can see it's a surface plot. This is actually just for help you to fine tune your system. Now, however, even now, the expert may not be satisfied with the system performance. You as a in terms of the system performance, either the customer or you as a system developer. So to improve the system performance, we may use additional sets. And that's why I've been telling you all along. So one way to improve the system is to have higher resolution, have more sets to describe that particular linguistic value. So in this case, we say that maybe we can do it by number of servers. We can increase it further to fine tune it further by having rather small or rather large included in your universe of discourse called number of servers. And then you, of course, once you extend this, you also extend the number of rules that you have. Once you increase just 2 sets, additional 2 sets of rather small and rather large, you find that the root now these are placed here, rather small and rather large, right? Initially, we only had 3, small, medium, and large. Now we want to include rather small and rather large into your number of servers. So basically, this one sits right at in between these 2 spaces to give you a better mapping or better coverage of your number of servers. So this one supposedly should increase your sensitivity, performance of the system, give you better accuracy. Now, by just increasing 2 additional values for your servers, this has increased the what called the basically it's a combination of your inputs, and it can increase from 27 now to 45 rules, right? As a result. So you can see just by increasing just 2 sets, you can have more rules to design. So as you can see in your assignment 2, you can appreciate that at the heart of your fuzzy logic system is the rules. And of course, designing the rules is not that easy. It's quite painful, as you can see here. So again, same thing, because I want to visualize, I want to see. Once I'm done, I will increase the sets to 2. What happens now? What do my rules look like? So this actually tells you the rules where to sit. That's all. You can see here. So number of servers I can increase by rather large and rather small here. So this is the output of my the rules. So now this is how you tune your fuzzy systems. So you first of all you review the model inputs, look at the input and output variables, and then if required, try to identify which are the ones which I think you should actually fine tune. Either in the case of the example, either I think in our case we can't do much because we only have 3 in values for the inputs. But you have too many, you can also consider decreasing the number of values here, right? And then if required, we define the ranges. This one what we did just now, right? We define by having these 2, rather large and rather small, for the number of servers. So you can also review the fuzzy sets. Now you look at inputs and output, and then we look at the fuzzy sets. And if required, as we did just now, put in additional sets. Now you have also you're also told that the use of wide fuzzy sets, where the base is very larger, may cause the fuzzy system to perform roughly. So it's not so accurate. So a thinner one, of course, is better. Right? A wide base fuzzy set may cause you some problems in terms of accuracy. This is the one I talked about before. So you're also advised to provide sufficient overlap between neighboring sets. So based on the previous work, right, it is suggested that the triangle to triangle and trapezoid to triangle fuzzy sets. Notice that we never talk much about the Gaussian. It's always the triangle or the trapezoid, right? So the amount overlap for such fuzzy sets, membership sets, will be between the range of 25 to 50% of the bases, right? It shouldn't be anything less and it shouldn't be anything more than 50%. But I think so far we also look at cases whereby there's no overlap. No overlap is actually quite easy, right? It's easy for me to design the rules, but once there's an overlap, it's quite easy, difficult. Now, how much overlap should I have to calculate those overlaps? So we should also consider that. Maybe play with no overlap, and then you try to increase the overlap. We can talk about if we increase the overlap, how does it affect my performance on my system? Ranging from 10% overlap to as much as maybe 40%. I will not go until 50%. I think that's too high. But again, you can test it out on your system. So review the next step is also can also review the existing rule and required add new rules to the rule database, right? So you find that maybe you can also add new rules to the database because the current system is not performing very well. So you can also examine the rule base. Now this is what you're looking at the opportunities. That's why this just now the block diagram, what you call these cube diagrams will help you to identify where can I improve. So you're examining your rule base for opportunities to write hedges rules, which is what very somewhat things like that, hedges to capture the pathological behavior of the system, to capture the behavior of the system. So just now we said just now earlier example, we actually added two more, which is rather small and rather large. You can also have rather small, somewhat small, things like that. So we play with those different hedges to increase your sensitivity of the system. This is part of the fine-tuning. As you can see, it is very troublesome to actually do fine-tuning, but fine-tuning you must, otherwise your system will not work very well. You can also adjust the rule execution weight. Some rules may have more importance, so most fuzzy logic tools allow control the importance of rules by changing the weight multiplier. So far, we have not played with the weights. We always assume it's always one. But in some cases, based on your intuition or the intuition of the experts. What do you mean intuition? Your gut feel. You think that this rule is more important than the rest, based on common sense. Right? So it still come back to the expert or your system. The same applies to your assignment. Right? You might want to play with the weightage for some of these rules. You say this is more important than this. As a result, I increase it to 1.1 as a result. Right? Finally, you can also revise the shape of the fuzzy sets. In most cases, unfortunately, I would say unfortunately or fortunately, in most cases, fuzzy systems are highly tolerant of a shape approximation. So the shape approximation will not give you much improvement. That's what it's trying to say, right? So it's highly tolerant. So even you change the shape approximation, you won't see much big change in your accuracy of the system. So so there was a case of your service center. Now to give you another example, a case study whereby in this case, I think I've seen it before I think you've seen before in the air conditioner systems that you have in the market today. So in this example, you're looking at the fuzzy controller for your air condition. So you have also your target temperature, and then your fuzzy expert system here will control the target temperature and the actual room temperature. So what is the output? Output is actually to either heat up the room. It means that you don't cool it down anymore. Cool it or no change. So very simple. Heat means that you reduce your cooling, right? Cool means increase your cooling. Of course, no change if you maintain. You don't do anything. So it's a simple system, but it's a good example for you to understand, better understand, appreciate your fuzzy logic system or fuzzy expert system. So again, you have to define your linguistic variables and the terms. This is at the start. Then you construct the metric functions as before, right? Construct the knowledge base of the rules, right? And then you convert your crisp data into fuzzy data now, right? Input itself into fuzzy data instead of say heat or heating on no cooling or cooling, and then no change. You change that into fuzzy data using the membership functions. This is part of the fuzzification process. Now, once you've done that, once you create the rules, then you have to evaluate the rules in your rule base, right? In your inference engine to see what is its performance. And then you can also look at combining the results of each of the rules to give you better results. And then you convert the output data into non-fuzzy. Okay, you need to also, once you've done that, right? You also need to tell the system what to do, exactly what they do. It can't be very fuzzy or very small, very large. What's the actual value that you want? So you have to convert based on the input. You can convert the suggested output from the system into actual fixed value. This is your non-fuzzy values using a process called the fuzzification, either Sugano or your Mandani method. So first step is actually define your linguistic variables. So assuming again, you can see 6 is an air condition, right? We don't have to worry about anything too cold, right? If it's too cold, humans will not like it too cold. So we believe that 16 is a good lower bound. Upper bound will be 34 degrees. Right? If it's more or less 34 degrees, I don't even need aircon. So 34 is a maximum. So that's why this range, because from the human intuition, from knowledge, from expert knowledge, you know that it can be too cold. Then if it's aircon is less than 16 degrees, you have to wear a jumper, wear some extra clothing. So we don't want to go into that 10 degrees temperature. Neither do we want to go into 30 and above, I would say, because 30 and above, I can actually turn off, open the windows and then go turn off my aircon. Because Malaysia, we have this kind of temperature, about 30 and above, right? So your linguistic variables are input and output variables in the form of simple words or sentences. So for this system, your temperature will be cold, warm, and hot, etc., which is your linguistic terms. Temperature here will look at very cold, comfortable, warm, very warm, and hot. So you can still see the same method of process. Now, every member of this set is a linguistic term, and it can cover some portion of the overall temperature values. See here, so I know 16 to 34, I break up nicely with a 3 degrees interval, ranging from 16, 19, 22, 25, 28, 31, and 34. So I can break it into very cold, comfortable, warm, very warm, and hot nicely. So up to you to find the best representation of each of these intervals. Now we can use the footnote, you can use the same membership graphs for both the room temperature and the desired temperature for convenience. Right? You can see because we are looking at the temperature, the actual temperature and the temperature that we want for the room. So basically we use the same membership graphs for both. So once you've done that, because of this, I can actually now divide nicely. So of course this is very ideal. Divide nicely into, I think for this temperature, air conditioned system, you can see I can divide it nicely into equal sort of overlap, and also the membership graphs. I can see nicely inserted in this whole area of 16 degrees to 34 degrees, nicely done. So then you know that in the left hand side, it's a trapezoidal, which is very cold. Then you have your triangular, cold, comfortable, warm, and very warm. You can also, if you want to, instead of using trapezoidal at the extreme ends, you can also use the triangle at the extreme ends. But normally, you find that most of the time, it is common to use trapezoid at the ends to represent the upstream parts of your membership, your universe of discourse, in this case temperature. Okay, so once you've done that, now you construct your knowledge base. These are the rules, right? So this is a matrix of the room temperature values versus your target temperature values that an air conditioning system is expected to provide. So again, expected means you have to talk to the expert to say this is my set of output expected of my air condition. So if you want very cold and the actual room temperature is very cold, right? There's no change over this diagonal. Now, on the other hand, if your target is comfortable and your system is very cold, so you should turn on the heater, right? Heat up the room itself, right? So that it will warm up to be comfortable and not very cold, right? And it goes on. So on the other hand, if you have your currently the actual room temperature is comfortable, but someone say, oh, I don't think it's cold enough for me. I'm going to turn on and make it colder. So I set my controller to cold. As a result, the controller will instruct the air conditioning unit to actually cool down further, right? So if it's from comfortable temperature, bring it down to cold, right? So this is your knowledge base. So once you get on this knowledge base, I can actually read it out for you. If the room temperature is comfortable and the target is cold, then the aircon should start to cool down the room, right? So on the other hand, if my room temperature is cold and my target is very warm, right? I need to heat up my room so that it becomes very, very warm. So I should turn on my aircon so that it becomes it heats up the room, heating. So there are two parts. For my this is actually very rough resolution. Only cool, no change of heat. You might also want to increase this further by having more values rather than cool, get a very cool or get a very, very hot thing to actually turn on the heater on your air conditioning unit. So this is what I said just now. So you can see here, based on this knowledge base, my rules will be 36 of them. If temperature is cold and the target is warm, then heat. And then if rule number 5, if temperature is warm and my target is warm, then no change, right? Obviously, so you can see this is a straightforward implementation of a fuzzy controller for my air conditioning unit. And of course, now, based on the 36 rules that we have, now, if the output, right? What is the output command? What's the actual command? How much the system should see from the logic expert system if the actual room temperature is 31.3 degrees and the desired temperature is 24 degrees Celsius. So if my actual room temperature now from my sensor is 31 degrees, I can see it's actually quite warm towards the other side of hot, and I want to bring it down to 24 degrees. Which rule or rules will fire? That would be a key question. Because we have so many rules here, which rules will fire? So we have to actually compute each of these rules and see which one will fire. Right? So this is your what is it? The input is 20. The actual room temperature is 31. I want to be 24. Right? This is my 31. This is my actual room temperature. It's kind of warm. I want to bring it down to comfortable of 24 degrees. Right? So you can see that it affects the comfortable membership set, and also affects also my very warm and my hot membership sets for my actual input. This is the actual output comparable, right? So you can see here, it will affect the rules which have this input. The temperature, actual temperature is hot, and the actual temperature is very warm, 31.3 degrees. So this one, I think we okay. So these are the rules that will fire, right? If the temperature is hot and the and the target is comparable, right? So this is the other one, which is the target temperature, right? Then the output, then the command to output is cool. Similarly, if the temperature is very warm, like this one, you see, intersects at this point, very warm, and the target is comparable, then cool. So you can see these two rules have fired as a result. Of course, you can also see that the rest of the rules also fire to some extent, because as I said before, right, all the other memberships will have a zero. So the zero can ignore them. Only those is non-zero. In this case, let's see some membership value of non-zero. This is about 0.1 and this is about 0.4, right? So these two rules will fire to some extent. Once you've done that, right? So you have your now identify the membership values as a result. Right? So here you have then you have your remember we said before in the I think the not the tutorial in the lectures. So this will give a 0.1 membership value and a 0.4 membership value for hot, and 0.1 for very warm, and a 0.75 for comfortable. This will be your membership values. So now you have this, you put these values inside the rules and see what is the expected membership value for the output of cool and cool. So as you remember, as some of you may remember, when you have this n function, what do? You take the maximum, right, of the two. All right? No, just checking on you whether you're paying attention or not. It's not, actually it's going to be the minimum of the two. So in this case, it will be 0.1 and your 0.4 of your cool. So you have two of these memberships, 0.1, 0.2, intersecting at the same membership of cool. So let's see how it looks like. Right, you have 0.4 and 0.1, right, of your cool membership. So now you have to classify it. Okay, this is cool, do nothing, and heat. Right, these are your three output memberships. So it only intersects at your cool, 0.4 and 0.1, because of the two rules firing with different membership values. So now with that, you use your center of what I call center of the center of gravity, the classification process. This is using Mandani. So you look at it and then you take samples from this range. The rest is all zero. Right? You take the samples. Say in this case, you take sample of maybe 0.1. So it's quite a fine resolution. Quite a lot of samples to take. So you take that and then you calculate your center of gravity, right, for your actual value to be classified. So once you've done that, you find that the actual value is 0.14. So you should maybe turn on your compressor to 0.147 in order to give you your output of cool based on the inputs of your actual temperature of your system, of your environment now, of the room now. Right? So it's how the system actually works to give you this value of 0.147. So 0.147 based on the center of gravity method of the classification. Okay, so just nice. I can see the time just nice for us to stop here. So what have we learned so far? In this lecture, which is the second part and the final part of your fuzzy expert system, we look at the fuzzy Mandani fuzzy inference method. How you actually compute or calculate the actual final output from your fuzzy inference system or fuzzy expert system. In addition, because of the limitations, some of the weaknesses of your Mandani method, which is actually takes a lot of time to compute, of course, but on the other hand, they give you better accuracy. But if you want speed rather than accuracy, you can also try the Sugeno fuzzy inference method. So we actually touch a little bit about the Sugeno fuzzy inference system and see how it can actually how it differs and what are the similarities between your Mandani method as well. So in the past 1 hour or so, we look at the two case studies. The first one is on the service center, whereby you want to keep your customer happy or satisfied based on your mean delay, how long the customer has to wait, how many parts do you have, or how many servers do you have, and how fast your people are able to repair the default or defective parts that the customer brings in. And if you actually advise, the system will advise you how many parts you should keep at the start of your operations. In the second example case study, we look at the more detail now, how the system will compute the output for an air conditioning system that has a fuzzy controller to control whether to heat up the system, the aircon, or to cool down the compressor, or cool down the air. So, okay, so that will end your topic on fuzzy inference system or fuzzy access system. In the next lecture, we'll be starting a new topic on, we'll be going to artificial neural networks. So we stop here for the mechatronics students. Because yesterday was a holiday, please be reminded you have a replacement tutorial and a lab depending on the groups this Saturday morning. So let's stop here. Of course, I welcome any questions you may have before we move on.
Sir,
yes.
For the assignment, right, we need to apply the neural network or not? For the
no,
lab,
I want to keep it very, okay, good question. I want to keep it very simple this year, right? I want to keep it simple this year. That means you only have to focus on the rules. How do you form the rules? By manually, not using any other tools. Because if you use other tools, of course, the good thing is that you don't have to worry about how the other methods work, just use it as a black box. But on the other hand, you also have to learn what these other, for example, the ANFIS, the artificial neural network enhanced fuzzy system works. So that one I did this year, this assignment, no. You just only have to look at the rules, look at the data, look at the rules, look at the data, and then try.
Again, we have only 2 points.
Using one method.
But the second point, we do not know the value of FV. We only know the first point. By V,
I think there's one paper in the handout
equal to 0.
the assignment package.
Also equal to 0. This
you can also look at how these other groups have done it.
So based on the equation,